Find the arc length from point B to point C in feet. In this problem, line segment AB and arc BC are connected at point B. The coordinates of point A, C, and O are provided, where point O is at the origin of the Cartesian coordinate system, and the north arrow points upwards. Also, the radius of the curve is given, as well as the bearing of line segment AB. Also note that line segment AB is not tangent to the curve. To find the length of arc BC, we can multiply the radius of the curve, r, by the interior angle, I. The problem statement provides the radius, which is 100.5 feet, but we still don't know the interior angle. In the figure, we'll define point O prime as the northward projection of point O onto arc BC. That way, we can equate interior angle I to angle BOO prime plus angle O prime OC, which we'll call angle I1 plus angle I2. We can determine angle I2 using trigonometry and by knowing the coordinates of points O and C. After plugging in the appropriate values, angle I2 equals 19.84 degrees. Similarly, we can solve for angle I1 using the coordinates of points B and O. We already know the coordinates of point O, but we don't yet know the coordinates of point B. We can determine the coordinates of point B since we know it is a point on the line AB and also a point on the circular curve, BC. The general equation for a line in two dimensions is y minus y naught equals m times the quantity x minus x naught. In this equation, y naught and x naught are known y and x coordinates for a point on the line, and variable m is the slope of the line in y over x. Since we know point A is on line AB, then we can substitute negative 62.71 and 247.65 in for x naught and y naught, respectively. Also, we know the slope of line AB is the tangent of the quantity 90 degrees minus the northeast bearing of line segment AB. So 90 minus 5 1/6 equals 84.83, and the tangent of 84.83 degrees equals 11.05. Now we have our equation for line AB, which simplifies to y equals 11.05 times x plus 940.6 feet. Next we'll solve for the equation of the circle, which contains circular arc BC. To do so, we'll plug in the x and y coordinates of the center of the circle for x naught and y naught, as well as the radius, r. After plugging in the appropriate values, the equation of the circle simplifies to x squared plus y squared equals 10,100 feet squared. At this point, we have two equations and two unknown variables. So we can solve for x by substituting in 11.05 times x plus 940.6 feet for y. And after some algebra, we get x squared plus 168.9 feet times x plus 7,105 feet squared equals 0. Now we can solve for x using the quadratic equation, where coefficients a, b, and c are 1, 168.9, and x equals negative 89.63 feet and negative 79.27 feet. These two x values represent the two x coordinates corresponding to the intersection of line AB and the circle which contains arc BC. From our coordinate system, x increases as we move from left to right. Therefore, the larger value of x represents the coordinate of point B. Substituting negative 79.27 feet in for x, the y-coordinate of point B equals 64.67 feet. By knowing the coordinates of point B, we can return to our equation for angle I1. Plug in the x and y coordinates of point and calculate angle I1 to be 50.79 degrees. Now we can compute the value of angle I by adding 50.79 degrees and 19.84 degrees, which equals 70.63 degrees. Lastly, the length of arc BC equals the radius of the curve times the interior angle swept out from point B to point C. In this equation, angle I should be in the units of radians. Therefore, we'll multiply 70.63 degrees by pi over 180, which makes I equal to 1.233 radians. After plugging in the values of the radius and the interior angle, the length of arc BC equals 123.9 feet. When looking over the possible solutions, the answer is A.